Hello everyone, my name is Nguyen, a PhD candidate at University of New South Wales, Canberra, Australia. So today I'm so happy to be here to have a chance to talk about our research. The title of my presentation today is Experimental Study of Flexural Behavior of High-Strength Steel Engineered Cementitious Composites, composite beam with profile steel sheeting. So here's the outline of my presentation. So first of all, I'd like to mention why we chose this topic. As we know, high-strength steel has been extensively applied in construction worldwide, from building to bridges, over the last several decades, thanks to its favorable strength to weight ratio. When high-strength steel applied in composite beam, it can help increase strength and create more spaces. It could also result in a reduction in member size and foundation. Moreover, the cost of fabrication, erection, and coating will be significantly reduced, and all of these will lead to a more efficient and sustainable design. Let's have a look at how composite beams work in reality. Composite beam consists of steel joint at the bottom connected with concrete slab on top through the means of shear connectors. Shear connector will guarantee the composite action between two components. At the second moment, concrete slab on top will mainly subject to compression, while on the other hand, steel joint at the bottom will be mainly in tension. Strength compatibility between two components help them work efficiently together. But when high-strength steel is used, much higher strength of high-strength steel compared to concrete lead to strength incompatibility between them. Some research have pointed out that a large area of high-strength steel beam has not been used when working, and the main reason for this is that concrete slab on top is prone to crushing much earlier than the attainment of high-strength steel yield strength. In other words, it restricts the blockage development of high-strength steel. Toward this end, there is a need to seek alternative materials that have the compatible strength with high-strength steel. It has been found that engineered cementitious composites that acquire compressive strain of at least 0.5% appears to be a promising candidate. The aims and objective of this research is to develop a high-performance composite beam using high-performance materials, namely high-strength steel and ECC, and second, to investigate experimentally the flexural behavior of high-strength steel ECC composite beam. Next, I'd like to move on to the experimental program. A total of two high-strength steel composite beams, in which one ECC named ECC40-140 and one normal strength concrete named NSC40-140 were cast, in which 40 denoted the targeted compressive strength of ECC or NSC in megapascal, while 140 indicates the slab thickness in millimeter. Both beams were constructed with identical cross-section configuration. High-strength steel beams at the bottom were designed to satisfy the compact section indicated in European standard and Australian standard. It was manufactured by welding high-strength steel plates together. To construct the ECC and NSC slab on top, one mix of ECC and one mix of NSC were used. The materials used for ECC mix included cement, fly ash, silica film, local dune sand, water, PE, and steel fibers. For normal strength concrete, cement, sand, coal aggregates, and water were used. Instrumentation setup is shown in this figure. On composite beam were tested under 4-point bending. A clear span of all beams were 3.1 meters, and the pure bending region between two loading points was 0.8 meters. 3 LVDTs were placed at the midspan and 2 loading points to measure displacement. LVDT 4 and 5 were pointed at interface between high-strength steel beam and slab at both ends to measure slip. 9 stringers were installed along the height of the high-strength steel section and 4 at the concrete surface. These were to measure the strain history distributed in the composite beam cross-section. The left-hand side picture shows the beam after casting, and right-hand side showing the test setup. 3 cameras were deployed to record crack, strain, and displacement history using digital image coloration. Based on similar tests of ECC and NSC, it can be clearly seen here that compressive strain of ECC shows lower value than that of NSC. That is 36 versus 52 megapascal. Minimum yield strain of high strength steel were about 750 megapascal. The load displacement relationship of tested beam is shown in this figure. For the ECC 40-140 beams, the load increased linearly until 432 kN with corresponding mid-span deflection of 20 mm, at which high-strength steel beam started to yield. That the stiffness of the beam will gradually reduce its load, and at the low of 546 kN, the first crack occurred near one of the loading points, and afterward, the load increased slowly until it reached the maximum load of 607 kN. At this point, the whole EC area in constant moment region was crushed, as shown in the left-hand side figure. Subsequently, the load decreased gradually, showing the ductility behavior. Similarly, the NSC beam showed linear elastic behavior until high-strength steel beam first yielded at its bottom flank at a low level of 445 kN. It exhibited the higher stiffness than the ECC beam, as the NSC yield had the highest elastic modulus than that of ECC. However, unlike ECC beam which saw the flexural behavior, the NSC beam fell brutally after reaching the peak load of 600 kN with corresponding midspan of 30 mm. The reason for the brutal failure was that the NSC beam exhibited the longitudinal shear failure near the support ends. This is a very common failure in an NSC composite beam utilizing high-strength steel, when the top NSC slab is not reinforced with the adequate transverse reinforcement. As the two beams have the same geometrical details and almost similar mechanical properties, it can be demonstrated here in that the EC beam is capable of resisting the longitudinal shear failure over its NSC counterpart. The load-slip relationship of two tested beams were derived and plotted in this figure. The average slip between ECC or NSC slab and high-strength steel beam were recorded using LVDT 4 and 5. It was found that the average slip of both beams were negligible until the load reached approximately 400 kN. Afterwards, slip increased to around 0.5 mm at peak load, which is relatively small. Slip at left end of NSC beams is higher since this beam subjected to the longitudinal shear failure. Based on the strain data obtained from strain gauge attack along the cross-section of composite beams, the load strain relationship of tested beam has been derived and shown in this figure. It can be clearly seen from the load strain relationship of the EC beam in the left-hand side figure that the bottom and mid-height cross-section of the high-strength steel beams were yielded and achieved at least 0.7% of tensile strength before EC slab crossed on top, with strain achieved 0.55%. Whereas for the NSC beam shown in right-hand side figure, only bottom flank of the high-strength steel yielded, with strain recorded around 0.6% before failure. It's obvious that a smaller area of high-strength steel yielded compared to ECC beams. So it is also worth noting here in that despite this beam fell with an aesthetic failure mode, NSC almost reached its maximum strain of 0.31%. Strain composite of tested beam were compared with the results obtained by rigid plotters analysis, European EC4 standards, and AS 2327 standards. Is it clearly seen here that for ECC beam, rigid plotters analysis results is pretty much similar to the test results, which demonstrated that the plotters development were rich in this beam. While for NSC beam, even though it fell in longitudinal shear failure, the NSC almost reached its ultimate strain. However, the result of rigid plotters analysis over-predicted the experimental results. Yes, several conclusions can be drawn from this study. A larger area of high-strength steel in ECC beam yielded compared to that in NSC beam. The high-strength steel ECC beam failed by crushing up ECC so in ductility manner, while high-strength steel normal-strength concrete beam underwent longitudinal shear failure, even though they were constructed with identical configuration and similar material properties. Strength capacity of ECC beam were well predicted by rigid plotted analysis and conservatively predicted by EC4 and AS 2327, which show the efficiency in plotted development of high-strength steel ECC beam cross-section. ECC demonstrated that ECC can be able to prevent the longitudinal shear failure that occurs in an NSC case, and this is apparently because of the high strength, high shear and tensile strength capacity of ECC. This is the end of my presentation. Thank you very much for your attention.